So now we're going to look at our last of 3 examples on re-expression of scatter plots and data that needs to be re-expressed because it's curved and a linear regression model is inappropriate. Whether you detect that from just thinking about is it straight enough, or from looking at the residual plots, or however you make that decision. So yesterday we looked at an example where we tried to predict the age of a lobster from the length of its carapace or its body shell. Today we're going to, and we also looked at how to predict the orbital period based on the distance a planet is from the sun. So today we're going to look at perhaps I think the most interesting example, which is trying to predict how many transistors there are going to be on a computer chip based on the date since 1971. So just a little bit of background information. Transistors are the computing components in a computer chip. They're what allows information to be computed more quickly or less quickly. So they're basically what controls the rapidness with which computations can be done by computers, and that's all of course done in the CPU chip. So just how many transistors, the more computing power. That's basically the idea. This started to become more and more prevalent after World War II, and by the 1960s, people at IBM had been working with refining transistors and making them smaller, and they discovered that that was the key to increasing the computational speed and limiting the size of actual computers, is making those transistors smaller and more effective. And so this guy named Gordon Moore was working in IBM alongside other luminaries of science and mathematics, like last year in Algebra 2, or whenever you took Algebra 2, you might remember Benoit Mandelbrot with the fractals. I think Gordon Moore was one of the colleagues of Benoit Mandelbrot. So there were a whole bunch of talented and revolutionary thinkers working at IBM back in the 60s. Anyway, so Moore decided that he was looking at how transistors were multiplying over time, and he said it was basically an exponential doubling process that basically was happening every year. So that's what we're going to investigate here. So I have a snapshot of the raw data. Let's get that into our calculator and continue looking at it from there. So those technicians like Benoit Mandelbrot and Mr. Moore, what was his first name? I don't remember his first name. Gordon. And Gordon Moore are, largely responsible for the information age that we're experiencing today. So Gordon Moore back in the 60s developed this idea. He looked at all of the explosion in computer technology, especially with transistors. That's what he was working with. And we'll learn more about transistors if you ever take me in physics. But he noticed that transistors were multiplying really, really rapidly. And this is the actual raw data up through, like, what's the last data piece in there? 2010, that's like a Xeon Nephlem EX, that's something from China. Some product from China. It's a really fast processor. Anyway, so we want to do what we've been doing, is try to predict if Moore was correct, and just try to make some predictions about where transistor technology is going to go in the future. So first we want to create a scatter plot. So if you're watching the video right now, I would get all of the data, that's only of course a partial subset of the data, and enter it in your calculator and scatter plot it, and that's what we're going to do here. So scatter plotting that data. I'm going to make sure it's in my lists. It looks like it is. Notice, I didn't enter 1971. Instead of 1971, I chose to go with 1. You've already got some really large Y values as you get into the millions and billions even of transistors on a computer chip. So you don't want to complicate your model and what the machine is having to do to create it, which we, by the way, have never even seen. It's quite a complicated process. You don't want to overcomplicate that and make it even harder and more unstable by using really large numbers for X that are, by the way, also all really close together, versus the Y's, which some of them are really small and some of them are really big. So there's a huge spread in the Y's, not so big a spread in the X's. That's going to make the model more unstable. So picking something like a smaller value to start with is easier for you and for the model. So you could pick 0, you could pick 1. I picked 1 because I wanted to match the digit, so I'd make it easier for myself. So 1971 was 1, 1972 was 2, 74 was 4, 8, that's pretty easy. 1982 was 12. My last one should be 40, let's go look. Because that was 2010. So this is years since what? I should put that in my data. 1971, not since 1970. If it was since 1970, that last number would have to be 41, that's a little bit sneaky, right? Okay, so we've re-indexed our data, that's what you call that. Let's scatter plot it. Scatter plot on list 1, list 2. I remembered that my zoom didn't work this time, so zoom 9. That's a different looking kind of plot, right? I don't think we've seen one like that. Is creating a linear model for it a good idea? Really not. Maybe you could do like 2 linear models, right? Like cut it right here and be like a line. We'd have to investigate that subgroup and see if it was curved in itself, right? It looks like it's straight, but that just might be the giant scale of our plot. This one even doesn't, by itself, doesn't look straight, does it? It doesn't look straight to me. So there's something else going on here. And we're just going to have to do the best we can, try to find the best fit. It's probably not going to be ideal, but we don't even need to consult the residual plot this time. This is clearly not linear. If you're not sure, consult the residual plot. Okay, so what do you guys think? Really bent, right? So you could try like a 1 over y transformation. I think we'll try a couple today. Let's try 1 over y first and see what that does. I didn't do that in my example, but it's really bent. Let's see. So should we go 1 divided by, what are the y values? List 2, okay. And then let's go and scatter plot list 1 versus list 3. Oh, and I want to keep track, just like we did yesterday, right? Keep track of your transformations. We'll say list 1, this is just x. And now we're going with list 3, which is going to be 1 divided by y, right? So, zoom out every time. Zoom 9. It definitely changed the plot, but that basically just reciprocaled it. Maybe we could do 1 over x and 1 over y. Let's try that. Or, there's all kinds of combinations to try. The more practice you have, the better you'll get. You don't have to be a master of this to do well in the AP exam. They usually ask you some pretty easy questions, honestly, about this topic anyway. Because this takes a lot of experience. So, I think this is more valuable not for the AP exam, but because of college labs. This is uber important for intro biology, intro chemistry, not advanced chemistry or anything like that. And a lot of you, if not all of you, are going to have those. So how about we clear this out. I'm going to try 1 over x and 1 over y. Just for grins, just to try it. Change my scatter plot to 3 versus 4. And I'll write that down just to keep track. I should have written this down to begin with. So list 3 is 1 over x. List 4 is 1 over y. Let's see what that looks like. Well, it's some kind of pattern. They're all piled up at the beginning near the origin. Can you guys see that? How close are they down there? Well, there's even a, can't you see the curve down there even, guys? It's a little curve down there, a little snaky. So that didn't work either. Crap. Well, I tried a couple more transformations for this data set when I found it. And here's what I ended up with. So I ended up with list 1 being left alone. And I tried a natural logarithm. And that, well, let's see if it does any better. So I'm going to clear these out. And list 3, I'll put natural logarithm of y. Uh-oh. Oh, I tried to put it in the wrong spot. There we go. So, stat plot. Just regular x versus the logarithms of the y's. All those other options we saw so far were terrible. This option's not ideal. Does it have some wavical stuff in it? Yes. But it's so much better than those other ones. We probably want to try a couple more before we settled on it, but I did. And I didn't find anything better. You might be able to. But this is about the best I could do without using a lot more advanced math on this problem. So, yeah, so I settled with that and said I'm going to just go with it. So what did my sheet ask you guys to do next after you picked a model? Oh, write it down. That's what the transformation is. What's the model? Well, we got to calculate it. So statistics, calculate, linear regression, careful. Use your cheat sheet right up on the board, right? List 1, list 3, and there's our model. So there's some stuff we know now. So now we know the natural log of y hat is going to be equal to, the slope is 0.3658. And see, there's huge numbers here, right? So, you know, I'm going to use a lot of those decimal places because I'm scared. 83583475558. I'm going to use all of them, in fact. We didn't do anything to x, and then we had a y-intercept of 7 something. I bet the y-intercept doesn't matter as much as the slope. So, okay, I also want to write down what r squared is. So if we were just using r squared as our only diagnosis, I'd probably say this model's pretty good. 98%, and some of you, a lot of you in that Tootsie Pop lab aren't writing r squared right. If you don't do that on the exam, like, you miss it all. So like r squared is the percent of variation, this time in the transistor count that can be explained by variations in the time or the years between technological evolution, if that makes sense. So remember, r squared is the percent of change in the y's that can be explained by the changes you're seeing in your x's. Don't try to write it another way. There are other ways to write it, but I doubt you're going to pick one, if that makes sense. So stick to that and you'll be good to go. All right, so that's pretty strong. We also probably want to look at what else if we're going to see if it's really good. Because we want to look at the residuals. The scatter plot itself even wasn't really that straight enough. We're just kind of doing the best we can with this one. Let's see if the residuals are really, really bad or just kind of bad, because they're not going to be good. So, let's see. So, edit. Let's make our residuals pop into list 4. When we're doing it the harder way, I said it's fine. If you want to try to do the residuals like the way you're supposed to, great. Here's the shortcut though. Where do I press? Second list. And there's your automatic residual maker. It uses the function that you currently have. Okay, so our shortcut to residuals, we're going to press second list and find the residual function, and it'll drop them for our current model, the one that's stored in memory at the current time. So now we want to graph what for the residuals. I should probably write that down. You could compare it to list 1. Could you compare it to list 2? No. Why? I transformed list 2 into list 3. So it makes sense to put list 1 there or list 3 there, but not list 2. Good. All right. No, sometimes there's different reasons to plot it against the x's or the y's. The book likes to do it against the y's a lot of the time. There's intricate reasons for that. You don't need to really worry about it. I'm more comfortable with always just putting x's there. So, good question. Yeah, don't worry about that too much. You'll be fine. List 4, right? So there's the residual plot. It was looking pretty good at the beginning, right? But then it starts to do a little bit. It's not awful, though. I mean, there is some kind of spread all over the place. It is doing this fanning out thing as you go over time, so it's definitely not great. But we haven't seen anything better. I tried several other models, like I said, and I couldn't get something better. So I think we're just going to have to go with this, and I'll tell you how to write your conclusion in a second to make it safe. All right. So next thing is use your model to predict the number of transistors in 2020. So how would I do that? Here's my model. What do I plug in? 2020? We transformed the times. It's not 2020 you should be sticking in.
No, it's whatever.
40 was 2010, wasn't it?
Yeah. Oh, 60.
It's 50. I should have written it down to begin with. Remember, we went years since 1971. There are 50 years from 2020, 1971. Okay? So now I'm going to stick that into my calculator and get it. That's going to be equal to the natural log of y hats, and we're going to have to do something to get y hat. So 0.3658. If I was smart, I'd have just downloaded this into my y1, but I wasn't this time. Okay. And, oh, I forgot. How do I solve this equation? How do I get rid of the logarithm? Exponential using its base. Natural log is a base of e, or 2.718 approximately. So you e it. So I got this. I got y hat, the predicted number of transistors is 1.028 times 10 to the 11th power. What is that in non-scientific notation? 3 is 1,000, 6 is million, 9 is billion. You guys should all know that. So if 9 is billion, then we're 2 more places after billion. So 102, comma. How many zeros are in billion? 9. And I could keep writing those digits out too, right? But I wanted to get you the point that this is 102 billion transistors that are predicted to be on a chip if this pattern continues, at least according to our model's prediction. So I should definitely get my units on there, right? And if you were writing this on one of my tests, you definitely want to write it in a complete sentence with full context. Okay. So, number 5, last question I asked on this problem was, even though this is certainly extrapolation, how bad is the extrapolation? I would call this a moderate extrapolation because it's 10 years outside our range, and how wide is our range? Our range was 40 years wide, wasn't it? So it's like a 25% beyond the fence extrapolation if you want to try to think of it numerically. That's a moderate extrapolation. So here's what I said though, and this is what I'd write in your guide, just for your own personal note, so you have an example. I said, I would feel safe using this prediction as a rough estimate It certainly can't be used as a precise estimate because of bad residual plot / extrapolation, those 2 issues. But I said I'd be comfortable using it as a rough estimate. It's about the best we can do. And here's what I said from science. At least an order of magnitude estimate, which means how much precision is there in that, what was it, 102, wasn't it like 124 billion transistor estimate? I don't care about the 24 so much, I care about the power of 10. The power of 10 is probably pretty safe. In other words, there's going to be some number of hundreds of billions. I was just saying hundreds of billions of transistors. If we have an estimate like we did a second ago, I'm going to write it down again, which is stuff, whatever that stuff may be, and that stuff is eventually multiplied times 10 to the 11th. Even if we're not super sure about, the exact specifications of that stuff, we know that it's on the order of 10 to the 11th power, which is in the hundreds of billions of transistors. So I think that the fact that it's going to be in the hundreds of billions of transistors, how many hundreds of billions, how many hundreds of millions added onto those hundreds of billions, in other words, all this decimal value in this stuff is probably not something our model is sufficiently accurate enough, sufficiently mathematically sound enough to be able to predict, but we're probably pretty sure it's going to be at least to the 11th power of 10 in terms of how many transistors we're going to have. So that wraps up this example. I'll see you next time.